Should I start? Okay. Thank you for the introduction. Um, I'm truly honored to be able to give a talk at this conference. I thank Professor Choi for that. Unfortunately, I'm not in Jeju anymore. I was there until this morning, but I had to come back. Couldn't stand eating past midnight or alone in Jeju anymore. Okay, so I'm going to be talking about quantum computing in drug discovery. It's not like we've been doing a lot of research in this regard so far, but there's a good possibility that in the future it's just going to be a really powerful thing in drug discovery. And the reason I say we'll talk about this from the past into future is because quantum computing in drug discovery is sort of like a future, but the past we have done a lot of research in the computational drug discovery, in particular application of quantum mechanical calculations. Of course, those are with the classical computers, but now I'm going to argue that how they can translate in the future. So, oh, by the way, my name is Archo. I'm from Korean University, but I also represent this startup company in Cerebro that we founded just last year. Okay, let me see how I do this. Okay, so let me start off with a very brief history about quantum computing. Back in 1981, Feynman basically talked about the idea of developing a machine using the laws of quantum mechanics that can do the calculations instead of laws of classical physics. He was just basically saying that okay, with the quantum phenomena, you can make it work as a computer. That was kind of a vague idea, but in 1985, David Deutsch actually developed the real concept of the quantum Turing machine, which means that it can be made out to be a real computer. This development was really slow, but in 1994, Peter Shor, who was an undergraduate student at Caltech, apparently taught by Feynman, I'm pretty sure, and he kept working on the quantum algorithm from a mathematical point of view, and he developed this algorithm that can factor very large numbers in polynomial time. Okay, so Charo, you wave, but that's not for me, right? Okay, all right. Anyway, in another very important quantum algorithm that was developed was in 1997 by Love Grover, who developed this search algorithm. We all know that we can do search with the computers with the current version. But in order to search the very large number of the data, it can take a lot of time. But the quantum algorithm can reduce it by basically the square root to the n complexity, which means that it'd be much faster when n is really now a large number. Now, along the way, although I didn't list them here, right around from 2000, there were a number of landmark the achievements that developed the real the physical quantum computers using these quantum mechanical systems. But finally in 2019, which is just last year, Google published a paper reporting that they had achieved quantum supremacy. What is quantum supremacy? That just means that for a given problem, the quantum computer will basically do something that the classical computer can never do in our own lifetime. And this is a very particular problem, and they developed this hardware and the algorithm for that. but nonetheless, it was done, and it kind of became a big news in this community. And since then, people have been interested in quantum computing a lot. Now I'm going to go back to the idea of Feynman about the quantum computing a little bit. He was once said that the real use of computer simulation of physics would be with quantum mechanics. He said nature isn't classical, which we'll all know. So if you want to make a simulation of nature, you better make it quantum mechanical. And he means that, okay, so, we have these quantum mechanical systems and all these phenomena. We can make use of these quantum mechanical laws that will help us do some calculations. So he was envisioning a computer with quantum mechanically behaving components. And in fact, these quantum mechanically behaving components are something that we have to run into as we develop the digital computer smaller and smaller. And if you look at just the memory chips, now we're able to put in a lot more data into the same size of the chips than maybe 10 years ago. But by doing so, actually, you're shrinking down the size of the chips and all these wires and all that. And now, if you, in fact, shrink it down to something that's comparable to atomic scale, then things will behave like a quantum mechanical. And now you actually run into problems in developing the digital computers in the classical sense. And therefore, in this sense, the technologically, quantum computers are basically natural extension of the digital computers, even with physical sense. Now, the people eventually came up with this idea that okay, so with the quantum computer, what's the difference between the quantum computer and the digital computer? And the fundamental difference would be in the memory storage. And obviously for digital computer, you talk about the bits of data, whereas the quantum computer, we talk about the quantum bits, which would be shortened to be qubit. Okay, so now if you look at the regular classical computer, the memory chips store information in binary integers. Okay, hold on. Let me, a pointer. Okay, let me just use a pointer here. Okay, so this is a very typical, the memory chips that's shown in this picture. And now the computers that we use these days are all 64-bit standard. So these are basically single integers in 64-bit. So it's all zeros and ones for each bit, and you represent a single number in these binary integers. So everything would be working with these integer numbers. However, in qubits, everything would be in superposition of two quantum states. And that's what they came up with for developing these quantum computers. Now, there's physical examples of qubits that's used and developed over the years. And the first one, and probably the most widely used at this point, would be the superconducting solid state, the circuits. Okay? If you cool down some, the regular materials, there'll be they eventually become superconductors, and in the superconductors you can do the squid measurement and everything that will give you a clear quantum mechanically behaving states. Something like the ions that are trapped can also behave like a quantum mechanical system. So that's another examples. And in more recent the developments, NMR on molecules in solutions, or even solid state NMR would be a good example of the qubit. You can use floating ions, but you use the laser to extract these properties of these ions that will behave quantum mechanically. Now, having said that, I'm going to talk a little bit about the data representation by qubits, and therefore what you can expect from the quantum computers. A single qubit can represent a superposition of two states. So although we notate it as 0 and 1, this is not like the regular bit where you actually mean 0 and 1. Here, you are basically saying the state 1 is state 2. Okay. Now, the qubit is a system, it's a quantum mechanics system where you basically have two different states, and you have superposition of them at each instant, and where these alpha and alpha 2 are complex numbers. Is a basic quantum mechanical formulation. And basically, these numbers will satisfy these relations where the modulus squares, sum of their modulus square will be 1. This means that a single qubit, the whole Hilbert space, not just the number 0 and 1, but the whole Hilbert space of dimension 2 to the 1th power can be stored. So if you have, like say, n number of qubits, then you will have this Hilbert space of dimension to the nth power instead of to the 1 here. And that's actually the continuous space where you can basically represent a lot of different things. And you know, of course, that in the laws of quantum mechanics, the measurement will destroy the superposition and will reduce down to a single state, and also on. But at least during the state of the quantum state, these things will hold true, and you'll always have the superposition of two different states. Now, the idea of quantum computing basically is using the quantum states or superposition of two different quantum states into one single qubit. So with classical digital computers, you will do the computation always with definite 0 or 1 per bit. So you can add, like say, 0 and 1, and you get 1 for that particular bit. But with quantum computers, these are always a mixture of 1 state and the second state. Therefore, the computation theoretically is always done parallel way. So that's the one thing. Of course, you know, the manipulation of these states would be something that you cannot imagine with the classical digital computer. But the people have developed these quantum so-called gates that will do the calculations in the supercomputers. There's one more very important the facts that we all learned from the quantum mechanics class that will come into quantum computing is what we call a quantum entanglement. Of course, quantum entanglement basically means that you have a two-state system. Knowing one state will determine the other state because of basically Pauli exclusion principle. And if you have that system, then you know, this will be a great asset. For example, if you do like the communication between 2 points, and knowing what this particular qubit is in the state, then you should know what the other side should be, and so on and so on. So these actually are all used in doing the quantum computing, and that will make things really, really fast, or something that you cannot imagine with the digital computer. The application of quantum computing has been realized in a few instances so far. And probably the most famous quantum algorithm in this regard is the Shor's algorithm, which I talked about in the very beginning. And this is to solve the integer factorization problem in very polynomial time. And when we say polynomial time, that means that it's much faster than what you would formally do in the digital computer way. Of course, the current state of the our computers can not even solve this particular problem in a short enough amount of time. That is to say that okay, if you are given a very large the prime number, then you would take like say 100 years to be able to tell if that's really a prime number with the current computer technology. And this the fact is a basis for what we call RSA encryption technology, and it's a way to encrypt data so that not everyone can figure it out once they intercept this signal. Right? So this encryption technology relies on the existence of a very large prime number. And since some eavesdropper cannot tell what that prime number is, you can make this safe. But of course, with this quantum computer and the Shor's algorithm, you can figure that out in reasonably a short amount of time, and therefore making this encryption technology useless in the future. So that's a pretty scary thing. So people are, in fact, trying to develop a new way to encrypt data. And once you get a hand on the real supercomputer that you use, then we should try to update this whole encryption technology altogether. Anyway, but the people have also talked about the quantum computing in drug discovery, and in particular, they always said that okay, developing these drugs, and if you use a quantum computer, it'll be much better and faster and all that. So there are a few startups that are claiming to use quantum computers to speed up drug discovery. But so far, the applications have been only for energy minimization or molecular similarity searches and so on. But if you want to be true to the original idea of Feynman, you really want to simulate the quantum mechanics. I mean, instead of doing DFT or Hartree-Fock and all that, and we talked about a few of those things during this conference, but we want to use the quantum computer to do all of that, and they will be faster and more efficient and all that, and eventually that will be like the holy grail for not just the drug discovery, but material science and chemistry in general. But then if you look at the computational drug discovery field, basically everybody only uses force fields and force fields based molecular dynamics and all the other kinds of algorithms. And so far have been quite successful. And in fact, the company that I used to work for called Schrödinger are recently made into a public company, and they made a big splash. And what they do is they use basically a computer to develop drugs, and they are succeeding. Just 2 days ago, they announced they have a deal with the Bristol Myers Squibb in developing the drugs. So are we good enough with the force field and MD? But it turns out that the QM, I mean, the quantum mechanics calculations, we all know is more accurate, although it is expensive, that you can probably make good use of that in biological systems. And in fact, that's what I've been doing last 18 years or more. And now I'm actually hitting almost these 20 minutes, but so I'm gonna go very fast about what I've been doing for the last 18 years, and to show you how this application of quantum mechanical calculation can help drug discovery. So first one, okay, let me just go fast here. Basically what I'm doing is that this is the drug molecule, okay, which we call ligand in this case, and the surrounding parts are the receptor proteins. And for those of you who are not familiar with what the drug is, let me just tell you that a drug is the small compounds, especially when we call them small molecule drugs. it's this compound that will bind to certain target proteins that will make things differently, and therefore curing disease and also and so on. So this is like a drug molecule, and what we're doing is to consider polarization effect that would be forced on the drug molecules by the surrounding protein atoms. Now, using the force field, you will not be able to describe accurately what this polarization effect would be. But if you use the quantum mechanical calculation, you change the atomic charges on these drug molecules, and therefore you would have a better understanding and the prediction for the binding of these things. And in fact, the example shows you how we exactly do that. This is the case of what we call a co-crystals, and its number is 1TNI in PDB. And it shows the native pose, which means that this is experimentally shown, the experimentally solved structure. Now, as you see, there are two hydrogen bonds here. This is an aspartic acid, which has a negative charge, and this is glycine. But now there is three the hydrogen atoms in this methyl group, but they all share in the same charge if you use just a force field charge here. So this is non-quantum mechanical, and as you can see, because of these the same charge values on these three hydrogen atoms, you don't see any particular treatment that from being close to aspartic acid, which is negatively charged. So now the prediction using this charge value would show the ring facing basically the other way, and therefore it's not the same as this experimental the structure. Now, if you apply quantum mechanics and solve for these atomic charges, now you see the one hydrogen atom that's closer to the aspartic acid will have higher charge value. And that's natural because, obviously that negatively charged residue will attract this, the charge thing, and therefore polarize this thing, and therefore has a higher charge value. And that's done by quantum mechanical calculation. Once you do that, and the prediction would be closer to the experimentally solved structure, just because we have the better electrostatic energy and the stable form using this charge value. Same thing can be done with the metalloproteins, where the metal ions are usually given the force field charge as a fixed one, but as you include this part along with the surrounding protein atoms, then we see that this charge value is dissipated around this coordinating the protein residues, and therefore has a lower charge value. And with that, now our prediction will be much more accurate. Now, going even further, actually, we did something called the QM energy scoring. And in this research, what we did was basically use the same QM calculation as you saw before, but instead of rescaling the charges, now you use the QM energy itself. And in particular, these kind of motifs are very ubiquitous in the drug discovery, where you see this, what we call a hydrophobic enclosure of these residues. And these are the phenyl rings, and obviously there's no charge or hydrophilic nature in here. Rather, these guys will be hydrophobic, but still there's the parts of the molecules that will be entrapped in there and interact with these guys, and that's what we call and the origin of these force is can be interpreted as a pi-pi stacking motif. And this is another example, and therefore we try to incorporate these interactions into the scoring scheme using the quantum mechanical energy itself. And with this idea, we were able to predict the binding of the protein and the ligand or the drug molecules more accurately, and therefore it can help drug discovery. But of course, this idea is on paper very good and accurate, but it's still too expensive for virtual screening, where you have to screen millions and billions of compounds. We couldn't generalize it to the drug discovery in general. Of course, we can put it in a small number of compounds where you do the optimization and all that, and it's okay to use this. But with the application of quantum computing, that's exactly what we're going to do. We're going to use these quantum computers to speed up these quantum mechanical calculations, and definitely get the advantages in drug design problems in using like many the drug compounds, the candidates. And now the people are saying, and also I agree with this, in the more realistic form of this drug discovery application of quantum computer would be in combining this quantum computer with classical computer algorithm, and therefore that's going to help our drug discovery projects in a not too distant future. I would probably expect maybe 5 years or a little more than that. We'll start seeing the actual application. And once it's there, it will be very fast and very powerful. So watch out. So since I'm passing almost 27 minutes already, so I'm going to stop here, and I'll take any questions if you have any. Thank you very much.
Okay, thank you for this talk, for this interesting talk.
Yeah, but you really never say anything about QC. I mean, for this particular.
Okay. Did I?
Any algorithm that is working, or at least they're trying.
Oh, I see. Well, like I said, I'm not an expert in a quantum computer itself, but basically they haven't tried these quantum mechanical simulation of quantum computers just yet. And we need to have a hardware at least like 108 predicted, maybe 170 qubits. But so far, the best we have is just around 50 qubits. So we haven't done the quantum mechanical simulations with the quantum computer yet, but there are algorithms where basically you're simulating these interactions of electrons with the qubits and so on, and that's under development. And so we will be able to use that probably in the next 5 years or so. But what I'll talk about today is that I'm not going to get into details of quantum computing application in the simulating quantum mechanics, because first of all, I don't know all the details yet myself. It's not there yet, but it will be there. And once it's there, I'm saying that you can use those algorithms to simulate what I've done using the classical computer and help in drug discovery.
Okay, thank you very much.
Any questions? It looks like there are no... probably Elfie Kraka wants to ask.
Yeah, thank you very much for this exciting talk. I have a question. When you think about the drug discovery process, let's say you have your quantum computer and you can do the QM calculations, you still have to start. So for example, you have a protein which you have identified for a disease. And then of course, the question is, how do you screen for drugs? So you could do, for example, just screening libraries, or
Right.
you could do a rational drug design where maybe artificial intelligence would help. So do you have any perspective how to combine this aspect then with the calculation?
Sure, that's a very good question, Elfie. So, and in fact, I didn't have time to get into this, but the current the state of the computational drug discovery basically involves the use of the AI. And in fact, my own company exactly do that. And what they do is, I mean, traditionally we have like the library of ligands. Okay, so we're going to screen them against a drug target, where you run basically this the binding experiment on computer using what we call the docking program, right? And then find a better match for that. Now we're at this point that of course we can still do that, and a lot of people still do that. And now the library have become a very large ones containing something like maybe up to 100 million the atom, ligands. But what some of these startups are doing using the artificial intelligence is to design from scratch. They basically artificial intelligence can put out some new molecules that you never seen before and try to match that with these target proteins using these traditional programs. But then basically through that process, you will actually do the more extensive screening. And of course, what I mean is that using the quantum computer at that point, evaluating how the newly designed, say, molecules will interact with this protein, the receptor, you will use this quantum computer to find these exact interactions along the way, and therefore you have a better prediction. But at the same time, you will have to use the deep learning and all these AIs to design this molecule, and also maybe generate these things using the classical computers. So that's why we say that you have to have some kind of combination of the quantum computer and the digital computer in this sense.